Hello. So today what we're gonna do, today we're gonna review some code, and it's a process that we do at UltraHost Entertainment, which is the company that I currently work for. And it's a process that we would do, somebody requests to do a task to implement some changes, and then basically, once the developer has done the task and has confirmed that the thing behaves as it should behave functionally, like if you're running in the game and you're supposed to do some jumping, that the jumping works just fine, and that has been confirmed by, let's say, game designers, then we move on to the technical review stage. And we usually do these technical reviews in such a fashion where we take two people, so that's the reviewer and the developer of the task, and then we just hop on a call. We use remote screen sharing and just go through the code line by line, basically analyzing it, discussing it back and forth, why things were done, how things were done, etc., etc. So you're gonna witness a review session like this, and we're gonna be doing a review with my friend Algimantas, who has submitted his solution to a task, which is it's a card game called War. You might have heard about it. It's a very simple game. We're gonna explain the rules, and then we're gonna do the code review. So the rules for the game are such. You're playing with a full playing card deck. So, it's, in case you haven't seen them, well, I guess you must have seen them, like playing cards. So it's a full deck without the jokers. At the start of the game, we select a trump suit, which is select randomly out of the 4 available suits, which are hearts, diamonds, clubs, and spades. And then we shuffle the deck, and each of the player gets half of the cards. Then what we do is basically we just take the topmost card from each player's deck, and then we compare to the values of the cards. So we compare the cards by their rank. 2 is the lowest, going to 10, then goes Jack, Queen, King, and Ace, with Ace being the most valuable, most higher cards. But trump cards are always higher than non-trump cards. So for example, if you have a trump suit that is hearts, even if you have 3 of hearts, that's still better than Ace of diamonds or any other suit than hearts. But if it's not a trump card, then you just take the card value and compare that. So the player who has the higher card just gets both of these cards, and if the cards are of equal value, so let's say 6 of diamonds and 6 of spades, then the players just get their card kind of back to their own score pile. And we just run through the cards. We play until nobody has any cards. And at the end of the game, the winning player is the player who has more cards. And an equal number of cards results in a tie. So now when we know the rules of the game, let's start the code review. And let's start with, so when you think about how to implement this, the first thing that I would personally do is I would start thinking about what kind of data types do we have in this problem, shall we say. So there's obviously cards, and cards are, well, if you take a physical playing card, it has the number on it, the value, and it also has the suit. And we have 4 suits here, and we have the values. So we can take a look at this type card, and there's a bunch of things here, but we can see card, and this has these 2 things, suit and card type. So let's take a look at suit. So suit is a sealed trait, which means the compiler makes sure that if you pattern match on it, you have to handle all of the cases. And we have 4 cases here, which is just right. We have all of the values listed here as a set because there's no intrinsic order in those. So a set fits just fine here. We have a show type class to make sure that we can render these suits. And we have these little nice UTF representations of the card symbols. I'm not sure I would put these.
No, I didn't put these. I'm not sure why they're there. On my computer, they didn't show any spaces. I'm using a Mac. It might be related to that.
Okay, so yeah, I guess let's ignore them for now. If I erase the space, it just turns into a less nice symbol.
Yeah.
So let's keep them for now. And here's basically an equality type class which says I know how to compare these suits. So far so good. Now let's go into the card type. And here we see that this is a trait which has these values listed. So we have Jack, Queen, King, and Ace. And we also have this number type. And here I would say this is a bit more overcomplicated than it should be. So it does use refinement types, and it says a card number is an integer which is, greater or equal than 2 or less than or equal than 10. But given that we only have like a very finite number of cards, we can just make it a lot simpler. And I'm just gonna erase this. And what we're gonna do here, we're just gonna do, can do this.
You're just gonna list all of each of those?
Yep.
Okay.
And then you can actually say,
Abstract class, abstract.
yeah, you can do this just to make it a bit nicer.
Mm-hmm.
So you have 2, you have 3, you have 4, 5, 6, 7, 8, 9, 10, and then we have Jack, which is 11. We have Queen. The final thing, I don't think it's really any. I think it's final by default. I might be wrong, but I don't think you can actually extend the case object, given that it's a singleton type. So you have just a listing like this. And why did I do this? Basically, every construct that you use, things from the advanced type systems like refinement types, they kind of carry this mental burden. And there's a principle, KISS, keep it simple. And the simpler the code is, the easier it is for the next developer or maybe you after a year or two to come back and take a look at it and see, I know what's going on, instead of putting a lot of effort into trying to figure out why and how things work. So yeah, in our case here, we also can just put all of these into a set as well, or a vector. So we can put all of them here. And we can actually just make sure that they're sorted. In this case, we can actually make this ordered because it has an implicit ordering that is, always correct. It has an inherent ordering. So we can always say we can compare it by rank. And if you take any card, you can compare it by its rank. So we can then just do sorted here, right? We don't need this anymore, and we can just say, values here, and say it's a vector of card type. So here we also have to now pattern match on all of these cases, which is, it's a bit boilerplatey, but still, it's simple, therefore.
Would you be able to just get the rank of the number, like maybe
Right.
match on all of them?
Well, I guess we can do like a tiny bit of abstraction here and say and we can define a trait and define that this has to go into the card type, and it basically doesn't do anything except it allows you to then do this.
Ah, okay.
And then we can say num rank to string.
Yeah, that's smart. Okay.
So yeah, so now we know that all of this is exhaustively matched. I don't think it will work like that, because this is an abstract class, and it's gonna have like this very weird type, so it might be a problem.
What does the compiler say?
It will probably say, if I try to compile now, it's gonna be problematic. Because we've erased a bunch of code, but maybe it will work. Let's try it. So we can optimize all of this out. Equals here is fine. Here I think
there's a better one, yeah.
From
ordering.
Yeah, we can just do this. Let's try compiling it. Because here, if you take a look at the card type, this type doesn't know anything about numbered. Therefore,
seems good.
We can do it like this, I think.
Did the compiler complain?
Did the compiler complain? Strangely, it did not.
Oh, cool.
Okay, so let's take a look and see if that works.
Just to see if all the orderings and everything works the same, you can run the a card type suit. This suit.
Oh, things seem to work. Okay, that's a bit weird. I'm trying to figure out how exactly it does it. So if you know that this is I guess it kind of is smart enough to know that all of the instances are listed here, and some of the instances do have this trait in them, therefore it can pattern match on them. Although I'm not sure, there's this exhaustive match. So we can turn on fatal warnings, and then I think it should make if there's a non-exhaustive match warning, which is a warning by default in Scala.
Oh, I'm using tpolcat's plugin for the default options, so it would by default have a compile error if a pattern match is not.
Yeah, okay, then it's great. So yeah, we have this, which kind of simplifies things a bit, right?
Mm-hmm.
Now we take a look at the card, right? And so the first question is, why is this a trait? Because a trait indicates that there's like a couple of versions of the card. And here we can see that there's a deck card, and then there's the trump card, which to me doesn't feel right. Because think about it like this, right?
Mm-hmm.
So you have a bunch of cards, and if you take a physical representation, if you take a physical version of this game, right? What makes a card a trump card? Is there some sort of marking on it?
Well, in the game, implicit meaning after you choose one. That's why the smart constructor that transforms a deck card into either a trump card or a basic card. And the game cards that are used in the game, deck cards that are only for deck manipulation.
Yeah, but I would say that this information does not really belong to the card. It's a how do you say it? So the problem is that whether a card is a trump or not, in our case, right?
Mm-hmm.
We pick that in the start of the game. But let's say we then want to add a new rule that if two players, reveal the same, the same card, let's say 3 and 3, we pick a new trump randomly, right?
Mm-hmm.
And suddenly you have a problem because you have a bunch of data that says this is a trump card, and now that preposition has been invalidated.
Yes.
And now you have to go, and in our case, this is a fairly simple game. But if you have a complex program, that data will be scattered all around, and now you have to somehow gather all of the places where that trump card is and recalculate all of that, right?
Mm-hmm.
So that's why I don't like modeling this as a part of the card's inner state, because what is the trump suit is more of a game property than a card property.
Mm-hmm. Okay.
And that's why I would say that the card should just be a simple case class, which is basically just two things, which, a deck card is.
Yeah.
And then all of this kind of can go away. And we can say, this can be this, and
You just leave card show in this particular case. You don't indicate is it a trump or not anyway. And the ordering doesn't make sense at this point, because on its own, it does make sense actually at this point then.
Yep.
Because it's contextual.
Exactly. So what makes sense is we still need to have a way to order the cards, right? But the order, as you said, is contextual. And it depends on the trump. Correct?
Mm-hmm. Yes.
And then we can say, so let's keep it like this for now. And then we can go back to the suit. And we said that suits do not have ordering, right?
Yep.
Unless we know what the trump is. And we can say order for trump, order for this, right? Then we can say order from, right? And basically here we have two things. So we have a one suit and another suit. And if these two values, if both of the cards are of the trump suit, right? Oh wait, this is not.
Yeah.
If both of these are of the trump suit, then it's equals, right? If the first card is of the trump suit and the other card is not of the trump suit, then the first card is greater than. And greater than is 1, if I remember correctly.
I think so.
Yeah. The other case is this is not a trump card suit, and this is a trump suit, and this is -1. And in the last case, we're also equal, right?
Mhm.
So now you have this ordering, and the card type has implicit ordering. Well, not implicit, intrinsic ordering. So now we need to figure out how to make an ordering for the card. And to do that, we basically have to combine these two orderings into one ordering. So if we take the definition, at first we said, we take the ordering for the trump, right? But this is the ordering for the suit. And then we need to, where's the map method? Do we have a map method here? Or will we need to write it?
Map method.
Yeah, I guess you can do this. This is the map method. I like to write a little extension. Let's write a little extension here. And let's just write map and basically say, given a function from A to B, we can provide an order. Well, it's actually from B to A. We can provide an order of B, and it's just using the same thing here. Just in a slightly nicer syntax. So we can say this and then say, okay, so this is a card, and from that card we can have a suit. So now we have an order that only orders by the trump, right? But then we have then we have to do the order for the other part. And I will write another method, another extension. And we're gonna say this is an order that, at first we're gonna try to order by this, and then if they are equal, then we're gonna order by this. And we can actually do that. Well, we can do that either explicitly or by using the derivation, I think. So, we can do that. I think there's like order, tuple order or something like that. Is there one? Maybe not. Let's just write it explicitly. Yeah, so we have two values, a1 and a2 here, right? We try to do order on them, and then if it's the same thing, then we're gonna use the another order, and if it's some other thing, then we're gonna return the other thing.
Okay, that looks smart.
And then we can just say, so that's one thing. First we order by the suit, and then, you know, if those are equal value, then we can order by the card type. And again, we have to do the map here and just do this. So now we have composed an order given a trump. Any questions about this?
No, looks really good. The only thing, I think it's not a map, it's a contra map probably, because it's from the left, but other than that, looks awesome.
It's probably should be named contra map. So now we have this. Now let's go and take a look. So we've reviewed this. Let's take a look at deck. Yeah, here we can just say it's just a card. Here we have a shuffled trait.
Yeah, I wanted to indicate that the deck is shuffled and only use a shuffled deck in the game, so you wouldn't get unshuffled games.
Probably there's, I'm not sure if this constraint is needed here. In theory, you could use this. So if you're using this as a marker trait, then I would remove the sealed constraint and just put it into something like a separate
okay, yeah.
File.
Package, yeah.
Because there might be, you know, not only decks that are shuffled, but maybe collections or byte arrays or something like that.
Yeah.
Yeah, so that's the initial deck, which basically just goes through all of the list, all of the possible combinations and creates that. Here we do have shuffle, which takes in the abstract context type, which needs to be a functor, so we could have map function of it. And then we also have the shuffler. I think, yeah.
Random does have a shuffle. The only reason I chose to use a custom typewise there is for testing, because in tests it's easier to just have a non-shuffled deck and just say the trump card is like on the like a first half, and then the other half, so those being the first half being the first winner, like a player one wins, and if you shuffle, if you don't shuffle and you say the suit that goes later, then the second player is the winner by default. Makes it a bit easier, although, yeah, might feel a bit complicated.
Okay, so yeah, do we need this? I don't think so.
I think. Okay, it worked out. Cool.
Okay, so yeah, this is a pure function. We give it random and deck, and then it returns a deck with shuffled. Okay, that looks reasonable. Let's take a look at player. Okay, maybe we should just do this and just replace this with card everywhere.
Yeah, the order card part doesn't work, but yeah, that's expected.
Okay, so it looks a bit scary for now. Let's take a look somewhere else. Okay, we have player 1 and player 2, which are not sealed traits.
Oh yes, they should. No, actually, no. These are just tags. So I would be able to tag things for player 1 and for player 2. That way, for example, player 1 wouldn't be able to use his own cards to evaluate the game by using his own deck and the other player's deck. It makes sense in the game file
We
later.
also had this. So
These are the implementations for the shuffling. It uses the random
yeah.
IO.
Let's go through, not rush through things, and let's go through them one by
Mhm.
one.
Sure.
Okay, so maybe let's go back to the player and see what this thing is up. So now we have player, which is parameterized by the player number, and basically there's two cases here, which one case is active player, and then there's the completed player.
That's like active game, completed game, player in an active game, player in a completed game. Naming could be adjusted.
Yeah, okay. Let's try to figure out a better name for this. Maybe finished?
Finished? Yeah, sounds similar, yeah.
In these cases, it's nice to just add comments like this, like simple comments. Player which has completed his game. Right.
Yep.
And here we have a player which still has
Some games to play.
cards to play, right?
Yeah.
And now let's take a look at all of this. Oh my, this is fun. So
We can go through that. Probably it's easier. I could explain it in context, and then we can go to other parts. I don't know, whatever you think is better.
let's take a look here at the game. So one of the things why I don't want you to explain things is that often when people read the code, right, they don't have you just laying around, and they read the code without any help, and the code needs to be written in such a way that somebody would come to the code, take a look at it, and hopefully it will make sense to him. If you need a guy following you around explaining it, it's probably not the best code there is, especially because you're gonna be the guy who will be reading the code after a year. And like, I had one too many conversations where it went like this. So what does this code do? I don't know, but you wrote it. Yes, half a year ago.
It was different me. It wasn't me. It was past me.
Yeah, exactly.
So
let's take a look into this thing. We have basically, again, a couple of cases here. We have the active game and completed game. And the completed game has two players that are finished. And the active game has, well, two players that are active. Pretty straightforward. Now we have an active game, we have play turn, and we say, okay. So we destructure the game into two players. We just take the next card, which is here. And basically we take the first element of the list, which we know that is non-empty, and then we add a tag to it that, hey, this card is of this player. and we get a card here. And basically the idea here is to statically discern which player the card came from. Okay, we have these two. And then we have this play turn method, which is, well, has a complicated signature to say the least. So let's analyze it bit by bit. So here you do this thing here where you take a card and you say this other card has to be a card that is not your card, right?
Exactly.
And you enforce that into the type system. I'm not sure why.
It complains if I don't if I don't use locally because I don't use the evidence in any way.
Oh yeah, you can do this.
Oh, cool. Okay, nice trick.
Yeah. For this, what we need is we need to take the order externally, right?
Mm-hmm.
And then you can compare those two. And then you can pattern match on the stuff and basically, yeah, if your card is bigger, then you get both cards. If it's equals, then you get only your card. Wait, why is it next card? Oh, it's
because it's your card and your card is the next card in your deck.
Yeah. Well, I kind of don't like that this logic is here. Because frankly, playing a turn probably isn't a thing that a player does here, especially given that you have kind of two players involved. And here, so let's for now provide an order. So the game doesn't know what's the trump, right? That's because your cards previously had that information.
Yes.
But in our case here, it probably makes sense to just know what's the trump suit. Kind of don't like this destructuring. I'm just gonna replace it with a simple property access. So now we have this, right? It's not terribly efficient, sort of, because you recreate it every time, but you know, that's a bit of a cost that we have to pay. You could optimize it by making a kind of composite data structure and putting both the ordering and the trump here, but you know, ordering is a function which isn't really pure data, so that doesn't really fit nice with the whole idea that case classes should only hold data. So let's just have it like this. Sorry. Yeah. Okay, so now see, you have this interesting thing where you have two players and you have to invoke the play turn for both of them.
Mm-hmm.
Right? And you give this card to the player one and this to that. And then you say, well, you know, what if there's this random case?
Yes. Yes.
which basically comes from the point that these players could have a different amount of cards, right? Nothing in the type system enforces that.
Yeah, I didn't find a good way how to get a way around this.
Yeah, and I would suggest that there's a way easier way to achieve what you're trying to achieve here. And I could say that we can just define this because we know that the game is for 2 players, right?
Yeah.
You can just say this, right?
Okay.
And then you can say this is a non-empty list of player cards.
Ah, okay. That's actually so obvious. Yes.
Now
Totally
it's
correct.
impossible to create a thing that will be out of sync, right?
Yeah, you're right. Yeah.
And well, I'm not sure why this is a method in the object instead of just, you know, being a regular object. But here we now have, we always know the answer, that there will be an answer. Here we can do a bit of a simpler thing, right? So we can say let's call it, I don't know, we can just define this. You know what? I'm gonna pause a bit and just rewrite. Using this because this is so much better, right?
Yes, much easier to read. The future you will thank you.
And for suit, for the card type, we had an intrinsic ordering. Okay, so yeah, now we have this. We just take these 2 cards, we do a comparison on them because we have this, and oh, it's probably we don't even need this method, but oh well. So now we have this, and probably we can just put it here and make it into a lazy value. And then we say, okay, let's let's take the cards, the first entry there, and compare them, right? Then we can pattern match on that. And this means the player 1 has 1, right? This means player 2 has 1. We can actually also introduce that, but I don't know. It would just mirror this.
Yeah, it would. So I think it's good enough.
Yeah. So we have these, right? And then basically we say, so if the player 1 has 1, then we have the, we can just say can say, let's convert this into non-empty list. And we have 2 cards here, right? We should probably name this. Let's name it, current turn cards, or something.
Yeah,
like
sounds good.
So yeah, this guy gets it.
Probably want some sort of separate storage or something, or marking of the cards. How are you gonna approach that?
Sorry, what?
You probably want to have a score deck or something like that for each player as well.
Yeah, so what I'm doing here is we're gonna do this, and then we're gonna do this, right? Actually,
Oh, okay.
it's a bit weird because to make the types to make the types work, we need to convert it from non-empty list to a regular list. We could have like 2 methods here as well. So for example, this and this, just to
list and
avoid this double conversion. And if the players got their own cards, then it's, you know, a list of current turn cards, player 1, and the second player gets his own card back, right? So that's player 1 gained. It's a list of cards that the player 1 and player 2 has gained, right?
Yeah.
Then we need to see if... Okay, so is there a tail here? No. Oh, I'm looking at the wrong...
Yes.
Yeah, so there's a tail here. And then we can see if it's non-empty or not, right? And if there's no more cards, then the game has ended.
Yes.
But if there are cards, well, then we can just create a new card, a new game. So we can do this copy. And here we also need the score piles, right? So we need, now we put the state of the players into the game. So let's call this player 1 score, and it's a list of card, and player 2 score. It's also a list of card.
Yeah.
And I guess you can, so previously in your solution, you had these markers of player 1 and player 2, which are here. But I think they're a bit excessive. Like, I'm not sure what do we get extra. I mean, I guess you can not put things into here, but the only place is in this method, and you're casting that card type into card with player 1 here. So if it was a more complicated approach, like a bigger program, and you're passing all of these things around, then yes, it probably makes sense to add this extra security. In our case, probably it's fine to just have this.
So because it's isolated in this one place, and we're okay just not really adding additional type information there.
Yeah, because if essentially here, you know, we would say so we have this and this, right? We have we have to take these cards and then put them into one or another pile, and then you do all of this, and you're gonna have the logic that tags them with these extra types is gonna be in the same method here. So it's the point of the tags is to carry the type information throughout the code so that you wouldn't get lost. Tags are very useful when you have, let's say you get an array of bytes and you're like, are these bytes compressed or not? I don't know. But if you tag them and you say array of byte with, compressed, then you know that you have to uncompress them before accessing them or something like that. In this case, there's not much use that you get from this technique, and it does complicate the code. Like it adds syntactic noise, and also you have to write all of that. So in our case, it's probably just fine to just kind of ignore that. So yeah. But, it could be added. So yeah, here we do have that. And if there's no more cards, then we can take this. And, well, create this player.
So instead of, because we sort of removed the necessity of players knowing of what cards to play, there's actually no point, no reason to leave this as it is now, because we could just, well, actually use the construct you created in the game that has like a scores in the game class.
Yep. So
yeah, if we just use player 1 score, player 2 score, just have that. That's good enough.
Yeah, we can just take this and put it here, and then just have it like this. And well, I guess we can delete these then, right?
Yes.
And in our case, then we say we have a completed game. And player 1 score. So this might seem obvious, but I like to do this just to make sure that it's harder to do something like this. It kind of annoys you because you see the difference.
We probably also want to add the result of the last game.
Oh, right, yeah, this thing. We can probably just introduce
extract.
We could use something like a state here, probably, but it would probably just be a bit overcomplicated. Okay, so now we do have, I think this can go away, right?
Yes, we don't need to do that. Yeah, we just need to create an initial game, which would be creating the construct of player cards.
Yeah, so boom, 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 boom. We do have a cards, and right, this doesn't need to happen. So we can just have this. Yeah, a part of the, so here we do have a deck, which we kind of know that it's of a size that can be split in half. So
we could add.
I would move this into somewhere closer to the, well, wait, we have this. Yeah, I would move this here, because essentially, if you do it here, right, the problem now is that this relies on implicit knowledge that the deck is of a certain size, right?
That's correct. Yeah.
And if you go and somehow change this, nobody will tell you go at this place and change it. Well, unless you have tests. But from the compiler standpoint, nobody will do that. So we found it to be a better option to just put these things nearby, right? Because if you're gonna change this type here, you will probably go through the methods and look through them, and then you're gonna notice this. Even better, it would be to write in the documentation that, hey, there's this thing here, or write tests.
Actually, we can add a constraint. Instead of using non-empty list, we could say that it's a list of cards that is that has a fixed size, that being 52. So
yeah, that's true.
Size 52.
That's 52.
And card value. You don't need the list because it's already a list.
Yeah.
And instead of non-empty list from list unsafe, in that case, we just
I think it's refine valid.
Refine V, I think. Yeah.
Yeah, there's also the macro variant, but we can't do macro variant here because, well, this is generated at runtime. So we need, and we also need to specify, I think.
You just need to specify the same type. So list card. So list card refined size 52. I think.
Yeah.
I don't think that's enough.
Yeah.
Yeah, it returns an either in this particular case. So before, I think it just expected things to work. So small change there.
Wait, let's split this into a couple of things and just say, okay, this is a list, right?
Huh?
And then we say refine, but don't remember. So we say no, that the type here is of a list. And I think it should be something.
I think it's just size 52. It's missing something, but I'm not sure what.
Let me open documentation of refined.
So in the for the collections, there's a size.
Yeah, because here it requires the refinement type, so and then there's this
Collections.
I think this has to be size and then exactly like exactly 52, which is equal 52.
Equal.
Yep.
Oh, cool. Nice.
Yeah, and in our case here we can just get else throw exception programmer, or not much we can do if we muck this up, right?
Yeah. Yep. I think shuffle deck takes the non-empty list, so we just need to be able to shuffle not only. So we need to be able to shuffle lists, which is, I think, the default of shuffling. So that's gonna be.
Yeah. Yeah. Also, this should be generic.
Oh yeah, we can make it generic.
And
Yeah,
to be fair, it should probably also
yeah.
be
If we do it
this.
like that.
What?
Okay, we can try. We can try. I think if we do it like CA, then we need to be able to convert from and to list. But yeah, let's try to implement that later when we get there. Yeah, works.
Pum, 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 pum.
Yeah, just value dot value. Oh no, actually,
No,
what does it say?
because we shuffle this, the refinement is dropped. So we need to, let's define a method. And put these two things there. Yeah, we don't need. Here we go. So now we have a method that allows you to refine things. And here, after we shuffle it, we drop the refinement because we dropped the refinement here. And then we have to kind of refine it again. And it is theoretically possible to write something that would not drop this refinement, but it would be pretty complex, I think.
Yeah.
So we can just kind of rely on this.
You could probably just make refine method private and just move the throw part there as well, so at least the code would look cleaner.
What? Sorry?
So if you move the get or else throw part to the refine method, make it private so no one else would use it. And then the code looks a bit nicer because you don't have to do the get or else throw in two places.
Yeah, but we also have this problem where now we need to
Okay.
we need to take this and say deck with shuffled.
It's not visible through your your video, what's happening on the right, but I assume you're doing the right.
All right. Let's do this. So this should be.
Yeah. I always like that.
Let's call it this and say refine list. And then we can use this and then
just act like that. Yeah.
So this is only possible because of JVM erasure, and basically because that runtime doesn't care what the type is, as long as you can invoke the required methods and access required fields on it. So you can take anything and add a trait that doesn't have anything and just cast it safely. and it works. So, for example, on C# and on CLR, this wouldn't fly. This wouldn't work because the runtime would say, I don't know that Deck implements this interface. You can't just do a cast like this. Okay, let's clean this up a bit. Yeah, and we have split in half. So yeah, because this is
now safe. Yeah,
pretty safe.
Yay, safe.
Where were we? So now here we can say, well, we can just say from split in half. We have these two, and then we say it's gonna be an active game.
Just zip them together.
Then we have a trump suit. Actually, in our case here, we should use we should return the list. We can return a non-empty list of player cards.
Yeah, that's true. That's fine.
Which kind of raises the question that, you know, we're doing this and to be fair, we don't even need this to be 52 exactly, right? We just need it to be even.
Yes, you're totally correct.
And also
positive, probably, but the list size doesn't get negative. So.
Yeah, we need it to be positive and even, because zero is also an even number. But let's keep it like this for now. And what we can do is we can basically just say grouped by 2, right?
Grouped by 2, it splits into 2 groups, like
it splits into lists of 2.
Okay.
So it's gonna be like player 1, player 2, or empty, right? And from that we can create this.
Nice.
And this is also, unfortunately, in the Scala type system, it's not expressed, but this is should be impossible to reach.
I think Shapeless has a default method that just says impossible or absurd or something.
Yeah. And then we say, again, we know that this should work, so let's take a look.
We're engineers. Yeah. Trust us, we're engineers. We know what we're doing. So.
Yeah. So basically now we have this, and in the game it's a bit easier. And then these two are just empty.
And that's gone.
And it's not an option anymore.
Because we're certain. Correct. Cool.
Yep. And now we have this result here.
Yeah, we don't need it. I think. Yeah, because the way we're playing the game changes. So yeah, this just returns those 2 decks. I think you have enough information to complete game. So. Yeah.
Well, I erased the result type.
So... Yeah, this is just tags the result for player 1 or player 2. I don't know. We could either tag it somehow or I don't know.
Well, I guess we can just do
Oh yeah.
I guess this
Is it
is
possible? Yeah.
this is simpler.
If their size matches, it's a tie.
Actually, we should probably not use this, but because these are lists.
Uh-huh.
Yeah, we have this. So essentially what it does is just a second.
Ah, okay. Wow. Okay,
Essentially what this does is if you say size, it will have to go through the end of the singly linked list. But if you do this, then it can abort as soon as it knows the result.
The result. Nice. Okay.
So yeah. So if player 1 score is greater than player 2, then the player 1 has 1. In this case, player 2 has 1, and in this case, it's a tie, right?
Yeah. We didn't use that to list an E method, but yeah.
It can be there. This one, right? We can delete that. Okay, so yeah, we do have what we have here now.
So shuffling.
Yeah, we do have shuffler. So we need to do this.
So you need to be able to transform C into list, and so then from list to a C, you need an isomorphism between them.
What else does this have? How can it shuffle things? Yeah.
For the time being, we could just limit it. Oh, okay.
What?
Oh, for the time being, we could limit it to list, but yeah, sure. Let's generalize it to something.
Do we have?
I don't think we have ice, so.
Let me Google it. Okay, and that's probably relating actual cats.
Actual cats, yeah, and ISIS.
Well, it says it doesn't have one, so we can just take
We
two
can make one.
functions.
Oh yeah.
Oh, whoops. So we have this.
we don't need line 51, no more refine invalid state, because we know it's correct. Yeah, just this. I think we still need a line. It becomes an equal, not a arrow. Yeah.
Yeah, now we need to. Now we would need to replace this.
Yeah, we can throw it out. We can not show the decks of the players.
Well, I guess we can just do this.
Yeah, that will work.
And do this.
Okay.
Now we need to update the IO and.
So we don't need the option because the state is always, I think, it will always conclude with a correct state.
Just a second, wait. Let's take a look here. One thing at a time. Here we go. So these are next cards. And this is player 1. This is player 2, right?
Hmm?
And here we have, well, again, I'm not sure why you wanted to do that. So this is a pure value now. And it's not really an option anymore, right?
Yeah, it's no longer an option. So no, yeah, simplifies.
So we can just do this and then do this and then have this. And it just simplifies everything, right?
Yes.
And so basically, let's go through what's happening for the people that might not know what is happening here. So you say you need to play the game and you give it the active game and you give it a way to print stuff. And then you define a loop which says we're gonna show the next pair, which is a side effectful action. Therefore it returns IO. And then you combine that action with the next action, which is just we take the current game and we play one turn. And then we see what happens. If the result of that is an active game, then we just take that active game and we feed it back to self, basically going in a loop. However, if that game is completed, then we just stop the loop and just return that completed game. So we know that this will always return a completed game, because if it's not a completed game, it will just go back into itself recursively. Therefore, you know that when you start with an active game, you will always end up with a completed game. So let's take a look here, right? So you create a random suit, you have a deck, you shuffle it, you create the initial state, you show it, you play, you get the final result, and then here you, again, it's just a winner.
Yeah, we can just print it nicely. And we're not going to show the deck.
Well, we can show the deck. We just need to do it a bit differently, because we had this, right? But we can do we can just do this.
Ah, you're right.
then in the tie case, we have this.
You can say it's a tie. Yeah. To list, I think, on the player one score because it's an or no, actually.
Yeah. So now here it requires a non-empty list, which we cannot guarantee because previously, now the game result is made out of that, out of these two things. Previously, it was encoded in these objects. But what we can do here is we can basically say, you know, this can be just a list.
That's true.
And also, it's probably pointless. We can just use this variant of sequence because there's no point in having many units.
Yeah. The list in these cases, and we're good.
Yeah. So, yep.
Cool. Let's try running the game. I think it should compile and work.
It doesn't compile here because here we have not provided these functions.
Yay, something happened.
So yeah, it works. So essentially, what I would want to kind of say from this whole review, sometimes it's not needed to use very fancy techniques. Sometimes you can express things a lot more clearly by just being careful with how you model the types. So, you know, instead of having fancy types, you can just take a tuple essentially, and that will enforce that both players have enough types. And we actually removed a lot of complexity from this implementation,
Yes,
right? There were options, there were some invalid states that should not have ever happened, and now all of them are gone.
Awesome.
Any questions?
Not for me. Everything seems quite clear and simplified. Learned a few things, so I'm happy.
Okay, so I guess that's a wrap, and that's it for this time. See ya, folks.